RF substrate, circuit board with copper cladding on the top and bottom, and sidewall was made of wires. These have been shown to be able to support modes very much analogous to rectangular metallic waveguides. If you don't know what I just spoke about, then CST is probably not the software for you, and I would recommend looking somewhere else. Now, when you start up CST, if you've used it before, you'll have a screen appearing like this with some previous projects on the right hand side and previous templates that you've gone through on the left, but for new users you won't have this. So I'm going to click on Create Project. It will give me the opportunity to work through a template, and this just helps to choose the best settings for the project at hand. We're going to go here, MW plus RF plus optical. That's the one that we want to use. And SIW is most like in the circuits and components. Basically, you just choose what you've got, what your project is, and the topic that it most resembles. Now, I know from past experience that waveguide couplers and dividers seems to work best. The settings here. If you are building some of these other things naturally, then that's will be what we want to use. We want to use the time domain solver. The frequency domain solver can also be used. I'll go through why that is in a few minutes. Dimensions, these are pretty straightforward. One thing that I would recommend looking at is here the dimensions of units of length rather in millimeters and frequency in gigahertz, particularly because of the ranges that we're going to want to be working with. Millimeters and gigahertz are appropriate. If you're doing something with much higher frequency or very much smaller, then you may want to consider using micrometers or what have you. Conversely, if you're doing a very large structure, centimeters or meters may be more appropriate. The frequency range, this can be adjusted later, but for the time being I'm going to go with 56 to 83 gigahertz. 56 to 83 gigahertz. You can set up field monitors if you like. This can also be done later, so I'm not going to worry too much about that for the time being. The last screen just gives you a little bit of summary. It's got this little _1 here because I've already got a template that I've used similar ones. So I'm just going to leave that for the moment and click Finish. Then CST generates a new project. This may take a moment. Okay, once it's done that, you have in the middle of the workspace, in my case on the right hand side, a list of some tabs: progress, messages, and parameter list. The reasons for these will become apparent in a moment. This may be arranged on the bottom if you're a new user. I think that's the default. I put it on the right hand side here just because it gives you a little bit more space to see a longer list of parameters, and I don't need all that much space for the design. Now, to begin building your model, 3D model of what you want to build, up here, the first tab is modeling. Now, SIW is built into a RF circuit board. It is a good idea from the word go to simulate your structures so that they can be manufactured. CST can simulate all sorts of weird and wonderful models, but if you can't actually build them, then your simulations will be for nothing. You'll be wasting your time. So this is something to bear in mind. Find out if you're planning on building any of these things, where you would manufacture them, what the process requirements are, what the limitations are, and do that. So this little block that I've just clicked here is called brick. that generates a sort of six-sided 3D figure, cube or a rectangle, analogous. And you can either pick points with your mouse, or you can press escape, which I'm going to do. And that brings up a little text box or message box into which you can type things, which will help in making our project a little bit more easy to maintain and modify afterwards. Now the name of the first solid, I'm going to call it RF substrate. You don't need to use underscores, you can use spaces, it's just a habit that I've gotten myself into. Xmin and Xmax, these similarly Y and Z, min and max, these show the range of your solid. It assumes that it is sort of perpendicular to the axes. The axes are shown here. I generally like to use X and Y axis as the plane in which the board sits, and Z being perpendicular to that. So I'm going to go type this minus substrate width over 2 Wyman length over 2 minus 2 and Zmin minus. Okay, so as I've typed there, I've used some variable names, substrate width, substrate length, and substrate height. You could also call it thickness if you wanted to. In fact, let me do that just to avoid confusion. And I'm going to name the component board. If I click on preview now, CST will bring up a new box telling me to enter values for these things. So I don't know what size the board is going to be. I can adjust this later on always. I'm just going to tell it that the substrate will be 50 millimeters wide and say 70 millimeters long and say 1 millimeter thick. I can go a little bit later and consult my list of sizes, but for the moment I don't really need to. Now, previewing that, you will notice that there's like a little faint orange line on the left hand side here. So if I click on the view window and I scroll up with the mouse wheel, scrolling with the mouse wheel adjusts to zoom, then that'll show me a little wireframe of what the board is going to look like. If I middle click, then it allows me to pan. Control and click allows me to rotate the view. Click and drag rather. Control and shift also allows me to pan. Alternatively, I can modify here in the bottom right hand corner what I want to do, but I find it most easy to use these shortcuts. I do not want to make the board a vacuum. I want to load a material from the library. Now again, this can be changed later. My instructions was to use Rogers RT Duroid 6002. So let's look for this. CST incidentally has a vast list of materials that are available. Here we go, Rogers RT 6002. I specifically selected lossy. You can simulate an ideal loss-free substrate, but I want to investigate the insertion loss for these substrates, so I'm going to simulate a lossy one, and it's a good idea in general to do that so that you can get a good idea of what your physical hardware will perform like. It will show you that the dielectric constant for this particular material is 2.94. The loss tangent is 0.0012. The loss tangent is 0.0012, and yeah, electrical properties measured at 10 GHz. This is a rather industry standard thing. Okay, load. So okay, and our substrate has been created. Step 1 is complete. Next step is to put metal on the top and the bottom. So I'm going to put another brick, press escape again, and I'm going to put metal on the top first. So I'm going to call it top metal. I'm going to make it cover the entire board. You can adjust this as well if you want to, but for the moment, minus substrate width over 2, substrate width over 2, and minus substrate length over 2. And for the Z, the bottom of the metal should coincide with the top of the board, so substrate thickness over 2. For the height, do substrate thickness over 2 plus metal thickness. CST can solve mathematical expressions like this, so it can be fairly powerful. The one consideration that you may want to make, CST does have the option of a local coordinate system. You can see the buttons up here. I don't particularly like to use it, but perhaps you might find that it's easier. Of course, we don't want this to be Rogers, we don't want it to be a substrate, we want to load a new material, and we want to use copper. Come down too far. Copper pure. Right, so that gives you some electrical properties of copper, electrical conductivity, the rho, and etc. etc. Load. If we preview this, it'll ask us, hang on, what have I done now? Substrate thickness. Should have entered this parameter already. Did I spell it incorrectly? Copy. Paste. Preview. Substrate thickness. That doesn't make any sense. What's happened? Why has this broken? Okay, doesn't seem to have broken. Strange little bug in CST there. It's just asked me for this substrate thickness twice. I'm not sure why it did that, but it seems to have recovered. Now, as you can see, as I have changed the value, so if I change the substrate thickness back to say 0.5, some values have been modified. Press Home, Edit Parametric Update or F7. So if I just hit the F7 key, and then it reads through the parameter list again and rebuilds the model, so it makes it thicker as well. Which is one of the reasons why parameterizing your 3D models are always a good idea. And then you can easily modify them so that you can simulate various different values. Finally, putting another brick for the bottom copper. looks right. The rotate, if you press Control and click and drag, then it is a bit finicky. You need to press somewhere on the model, and then it uses that as a pivot around which you can rotate. So if you get it wrong, sometimes you find yourself looking at something that you didn't expect to. Once you get used to it, it's not so bad. Right, so now we have a board with cladding of copper on either side. It is 50 millimeters long. I'm just going to exaggerate this a little bit and make this 70 millimeters long and 40 millimeters wide. 7. Okay, so it's very clear which is length and which is width dimension. Right, so the next component of SIW is the via to make the sidewalls. Now the vias are going to be running along this way, along the length of the SIW. And in order to make those, you click this button over here, cylinder. Same procedure as last time, except that the box is slightly different. Now, the name, I'm just going to give it a name, via. Orientation means in which axis the plane, or the axis, what would you call it? Anyway, along which axis is the via going to run? It's going to run along the z-axis, which means it's going to go up and down. The outer radius, I'm going to call it via radius. Inner radius, I'm going to leave it 0. X center will be. Now you're going to need to do a little bit of thinking, a little bit of planning in this case. From experience, I know that you need to do something a little bit like this. Substrate SW, okay, minus SW width over 2. Y center. So X center is where along the x-axis this via is going to be. Now at the moment, minus SW width over 2. SW width is a new parameter that I have just made, and it's going to be somewhere arbitrarily along here. The Y center, I want to put it down here at the front. I want to make it minus substrate length over 2 plus 3 times via AD. That's just to keep it a little bit away from the edge of the board. Zmin minus substrate thickness over 2 minus metal thickness. So this cylinder is going to go right from the bottom straight up to the top. 2 plus metal thickness. Okay, I should point out at this point that your parameter names do need underscores. They have to be all one contiguous thing. You're not allowed to use spaces. The names of your components can have spaces if they want to, but not your parameters. Okay, segments. If you use 0, it tries to approximate a circle as close as possible. If you use some other number, 3, 4, 5, or higher, it approximates a circle with a n-sided polygon, where n is the number that you put in here. Okay, so if I click preview, it's going to ask me for what the via radius is. You will need to do this according to choose this number rather according to the capabilities of your factory that's going to manufacture the board, according to the drill bit sizes that they have. It's also usually a good idea to simulate for a few different drill bit sizes just to determine whether or not that has a big influence on your design. So I'm going to go ahead and say 0.2. That's a fairly typical value. The SW width, now to work at, say for argument's sake, we want to work at this frequency, sort of 56 gigahertz. There are analytical equations that you can get a first order estimate, or even actually a reasonably accurate estimate of the width of the SIW, and they're related to the equations for the sizing of a dielectric filled waveguide. Now, you can go and look those up if you like, and I recommend you that you do. For the purposes of this video, though, I'm just going to guess, and I'm going to say perhaps that the SIW is 10 millimeters wide. And we should see a little via here presented for our view. Now, it's sort of disappearing away into the material underneath. So if we come up over here, okay, it won't let us do that until we're finished with this. Let's just click OK. And see, make a circle there. On the navigation tree, if I navigate to RF substrate and I click on it, then it's highlighted. It sort of makes the other shapes transparent. And it highlights this one. So for the purposes of building, to make everything a little bit easier to see, I'm going to hide the dielectric board. So you'll notice that it's hidden in a way. It's still there, and when it simulates, it will simulate properly, but it's just not visible. So now you see we've got two plates of metal with a metal cylinder connecting the two as a wire. Now, I usually leave the inner radius as 0 to make the CST simulators a solid cylinder of copper. Because of the skin effect and other things, this doesn't really make a difference, even though wires are usually just holes that have plated metal on the inside of them. So they would only have a very thin piece of metal, and on the inside would actually be air. But for the purposes of simulation, that very seldom makes a difference. Now, it would be very tedious to have to go and place each of these wires by ourselves manually. Fortunately, CST has a transform command. So the first thing that I'm going to do is translate to mean move it around in a direction, and I'm going to say copy and unite. What that does is, instead of making 100 little wires and each of them coming up in the list over here, it joins them all into one entity. Repetition factor, this can also be a mathematical expression. So I'm going to make this substrate length divided by wire spacing minus 1, just so that everything fits. The translation vector, it will be in the y direction of wire spacing. Now if I preview, it's going to ask me what the wire spacing is. I'm going to define this in terms of the wire radius. General SIW principles suggest that your wires should be spaced at 4 times the radius or twice the diameter, to ensure a minimum amount of wires and also a minimum amount of losses. Okay, preview. Okay, so you'll see there that it's made a length of wires all the way down, and no, it looks as though one of them is still sort of jutting off the end of the board there. So I'm going to make this -2. Preview. Right, that's fixed. Apply. Now what I want to do to make the other side of the SIW, the wires down the right hand side, is I'm going to say mirror. Copy unite I'm going to leave. Repetition factor 1. Now mirror plane normal. Around what plane do I want to mirror it? I want to mirror it around the YZ plane. That means I'm going to use X plane normal 1, 0, mirror plane normal. There. And the center can be the origin. That's fine. If I click preview, you'll see that that my guess was correct. That X plane is the one that I want. Sometimes I get it wrong, but in that preview tool is useful, that it just shows you what is going to happen before it actually happens. Okay, so click OK there, and now I have a section of SIW. Right, so now I've got the 3D model. Now what? I have the opportunity to parameterize things, to change things a little bit, and the model will adjust itself accordingly. Even the wire radius, for example, if I make it a 0.3 millimeter radius, then press F7, the size and the spacing and even the number of wires will have adjusted themselves accordingly. Because this is an integer thing, sometimes the spacing between the board edge and the last wire is a little bit unsatisfying. So what I generally do is sort of shorten by maybe a millimeter, 69, just to make things look a little bit even. If you have a more serious design, you want to be a little bit more rigorous than this, then you can. If your design is a little bit more serious and you want to be a bit more rigorous than this, then you can. But for most purposes, I find that this works just fine. Right, so to go about simulating this, the simulation tab at the top is where we'll find the tools we want. The frequency range we've already chosen. The background we do want to choose, however. Now, material type, we do not want PC, we want normal. PC stands for perfect electrical conductor. Normal means just a normal air, vacuum, whatever the case is, normal space. Click OK. Boundaries is another important thing. Now, the bottom, I'll look at that first. We want the bottom, in other words, Z-min, to be an electric wall. What does that mean? Well, essentially, we want our bottom plane to be a ground plane. We want the tangential electric fields to go to 0. That's what it indicates there, ET. In the X direction, X min and X max, that's fine. Think about what would happen in a real situation. You wouldn't have really anything on either side of your PCB, it would just be open. The top, however, would normally be open as well. So that is Z max. What I normally do there is open add space. And then what CST does is it adds a little bit of space above your model according to your frequency. Because we're at 56 sort of gigahertz, the space is quite small. If we were at a lower frequency, say 500 megahertz or 1 gigahertz, you would see that it would make quite a bit of space above. In a waveguide simulation like this, it doesn't really make that much of a difference, but when you incorporate your SIW with other structures on the board, such as Microstrip, for example, they would be interfered with if there was an electric wall, say, on top of the simulation, on the top boundary of the simulation, rather. So, to keep it consistent, I think this is just better. And the Ymin and Ymax are going to keep electric walls because I'm going to put waveguide ports there, and we'll see what happens there in a moment. Symmetry plane, it is nice to use the YZ plane as magnetic symmetry. What does that mean? Well, the magnetic fields on either side of the Y axis are going to be symmetrical. That means that it saves us a little bit of computer time because the software only needs to simulate one half of what it would otherwise, and for the other half it just copies what it simulated on the right. Now click OK. I think that is it as far as the settings go. Then we need an input and an output port. Okay, so we do that by clicking the waveguide port. CST always guesses wrong. Perhaps it thinks that the default axes are the ones that I don't use. In any case, we want ports to be normal to the y-axis. I want to start out with port 1, and yeah, positive orientation. So it's coming from the minimum y and it's pointing towards the maximum y. I do not want it to be a full plane port. I want it to have free coordinates. And so the x-min will be minus SW width over 2, and y-min will be, x-max rather, will be plus SW width over 2. Okay, you'll notice that in the preview window it has shrunk the port to the size of the SIW. That makes sense. Y-min, I want it to be minus substrate height over 2, and Y-max there we go, I caught myself out. Minus substrate thickness over 2 and substrate thickness over 2. There we go. Okay, so having a bit of a closer look, we see that the waveguide port has inserted itself nicely over there. If you want, you can make it a little bit wider to include the metal and the length of the wires. I find that this doesn't make a terrible amount of difference, but you can experiment with it yourself and find out. Don't worry too much about the other stuff for the moment. What I am going to do though is add another mode. So there'll be 2 modes here. I want to simulate because of this, and I'll come back to it in a moment. Okay, click apply. Then it will go automatically to port 2. And for some reason, CST is a little bit buggy. That even though it had Y selected, it was pointing in the Z direction. Anyway, never mind negative. So you'll see that the negative port has appeared on the other side. If I flip the model around, it already has the right sizing because it's kept it from what we did in the first time. It already has 2 modes. So we just click OK. Right, so I think that is it as far as our model goes. Now, what I'm going to do first is here, click Setup Solver. Accuracy of -30 dB, that has to do with the way that the time domain solver works, and we'll talk about that in a moment. What I want to do first is have it calculate port modes only, and I'm going to let it start. In the meantime, I'm going to explain. So now if we click over and look at the progress tab, it'll show you how far it's getting. Now, because it's doing port modes only, it won't take that long. What happens in the transient solver, the time domain solver, is that it puts an input signal, and here under 1D results, when we've actually done the simulation, you'll see it in at the one end, and then waits at both ends for the signals to come out. If your frequency range of the simulation is below the cutoff frequency of your SIW, then the energy will just sort of bounce back and forth. The waveguide will cut it off. It won't propagate down the waveguide, and it'll just bounce back and forth here in a sort of a resonant kind of structure, which means that the time domain simulation will take a very, very long time. So you want to check that you are operating above the cutoff frequency before you start the setup the solver properly. Now, to see what it's got, here in the 2D, 3D results, port modes, port 1 or port 2 will be the same, E1. Now it'll plot me a little bit of a electric field, and that looks exactly like a TE10 mode. You'll notice here that the F cutoff is 8.7. So that means 8.7 gigahertz, and my SIW is far too wide if I wanted to go for 56 gigahertz. Similarly, E2 means the second mode. Now the second mode that will propagate, because SIW is reasonably symmetrical, unless you deliberately excite it, will be a TE30 mode, and its cutoff is at 26 gigahertz. Okay, how to rectify this? Well, let's make the board a little bit, or the SIW rather, a little bit smaller. Go back to the parameter list. I'm going to make the wires a little bit smaller again, 0.15. Yes, okay, if you change the parameters, obviously the results are no longer valid, so you need to delete them. Then SIW width, I'm going to change that to, say, I guess, 4 millimeters. Press F7 to update the structure, and you'll notice that it's now very small. Okay, let's try again. As I said, if you'd used your analytical equations like good Boy Scouts, then this wouldn't be too much of a problem. Okay, now we're getting a little bit closer, 21 gigahertz. Looks as though this SIW is going to be very, very narrow for these high frequencies. SIW width 2 millimeters. Try again. Okay, now it's looking very narrow. Okay, it's finished again. Port modes, port 1, E1, F cutoff 43. Okay, so now we're in the sort of the right order of magnitude here. Generally, if you're working with that sort of thing, you want the cutoff mode to be sort of your minimum frequency of interest divided by 1.25 to give you enough headroom so that you don't have any of your signal that's lost. 56 divided by 1.125 is 44.8, and we see that the cutoff frequency is 43.6. That's, for many purposes, close enough. The next mode has a cutoff of 128 gigahertz, and that is well above the limit of 65 gigahertz that was imposed. Okay, so the process is iterative, and you would go through it like this. So now we're certain that the cutoff is where we need it to be. We're not simulating over any cutoff modes. Frequency range again, make sure that that's fine. Back to setup solver. Actually, wait, hang on, before I do that. Once we've established that the second mode is not going to interfere with us, I'm going to go back to the properties of the ports and reduce the number of modes to 1. So it will only propagate the first mode, or rather it will only simulate the first mode, and it'll save us some computing time. If you're doing just one run, then this doesn't make much of a difference, but if you're doing parametric sweeps or optimizations where you have lots of runs after each other, this can save you a lot of time in the long run. Okay, setup solver, we uncheck calculate port modes only, and we click start, and it will start to mesh the model and then compute the cutoff. So what you may like to do is click on mesh view, and that will show you how it is discretizing the model for simulation. Now, an interesting thing about the time domain simulator, or solver rather, is that the first 3 mesh shells after the port need to be homogeneous. Now, luckily, because we are at such high frequencies, the mesh that it's generated has 3 first homogeneous cells, although you may notice that these are a little bit thinner than the ones over here. CST is a little bit clever in that way. Sometimes it can't do this by itself and you need to manually adjust the mesh properties. You do that by clicking on global properties and adjusting the number of mesh cells per wavelength. You may also just need to extend this a little bit or make one of these vias rectangular deliberately and push it up straight against the port, just for the purposes of the solver. That's just one of its eccentricities that it wants. The frequency domain solver doesn't require this, but it is a little bit slower in these sort of circumstances. Okay, so you'll notice that it may take a little while. It gives you a bit of an estimated countdown of how long that it may take. And if you're working on a laptop as I am, you may notice at this point that the fan starts blowing and it starts to get pretty hot. So it is working quite hard. If you fire up Task Manager and click on Performance, which may take a while, you'll notice that it's revising its estimates reasonably quickly. It's coming down, so it won't really take 500 seconds usually. With one exception though, performance. So you see the CPU usage graph is quite high and it's using a lot of memory as well. Yeah, it's using transient solver in 64-bit mode. Okay, so transient analysis 1 of 2. It does 2 because it does 1 from each port. You can tell it to use S parameter symmetries, in which case it usually only does 1. But if you want to be really accurate, then you uncheck this option. The one exception, in which case transient solver will struggle, and you will see huge numbers here, is if you are simulating over a cutoff frequency and the energy starts to bounce back and forward. What the transient solver does, and it's useful at this point if you understand a little bit of computational EM, I found that even just the limited knowledge that I had, a little bit of reading that I did, helped me to understand what CST was doing. So the modes that are not passed or not propagated generally bounce back and forward within inside the waveguide. The transient solver works by putting in a signal at the front and listening and seeing how it comes out at the end and at the front again if there are any reflections. It does a numerical technique based on Maxwell's equations, and it waits for the signal to die down past a certain threshold. So that option that we had, accuracy minus 30 dBs, it waits until the signal in all the cells is 30 dBs lower than what it was, or that rather than the amount of energy that you put in the front in the beginning. And with a cutoff, if you simulate over cutoff, then this stuff just bounces back and forward. If you simulate over cutoff, the stuff just bounces back and forward and it never reaches that. Well, it does eventually reach that minus 30 dBs, but then your results are wildly wrong. frequency domain solver uses a phasor-based technique, but it has to do many frequency samples. So particularly if you're doing wideband applications and non-resonant kind of stuff, it does take longer, and it is better to use the transient solver. And if you want to obviously verify the response of your waveguide structures over the cutoff region, you should use the frequency domain solver. But if you're doing parametric sweeps or optimizations, then I would suggest that you limit your frequency range to the modes that pass, and do that. And then once you've optimized your design, then it'll be done. Okay, so that appears to be finished. It hasn't taken too long. So here under the 1D results folder, a number of things have shown up, and you'll see this is more or less what I explained. This is the signal that was input, and then this is the signal that it saw at the output 1 and at the output 2, and from these it calculates S parameters. Now this is more or less what we expected. S21 and S11 are basically the transmission. S21 is what port 2 sees as a result of what was put in port 1, and port S12 is exactly the reverse. It is what port 1 sees as a result of what was put in at port 2. S11 is a measure of how much reflection there was, and for a microwave structure, this sort of minus 20 dB level is pretty good. The insertion loss that we were asked to do, insertion loss, is found specifically in S21. This means that over this frequency range, the insertion loss is roughly sort of between 1 dB and 1.6 dB. You'll have to determine whether or not this is suitable for yourself. In SIW, this varies according to various things. For example, the thickness of the copper, the height of the board, and the dielectric constants, etc., and the loss tangents of the board, according to relations that have been derived in the literature. And I would suggest that you go and look these up if you're planning on doing a comprehensive study. I think that is all that is needed for now. Right. Okay, so the next thing that you will likely want to do is a parametric sweep. If you want to run the same simulation over a number of different parameters, new sequence, new parameter, say you want to sweep SOW width, linear sweep, or logarithmic sweep, or arbitrary points. If you have specific points that you would like to use, for example, these board heights, then substrate thickness, arbitrary points, and I'm going to just copy and paste these numbers. 0.17, there's a semicolon, 0.254, there's a semicolon, 0.508, there's a semicolon, so do the first 5, 6, this clump. Okay, right, so if I click the check button, yes, delete the results, then it will run through this sequence and show me what it looks like. There's the narrowest one, a bit thicker, a bit thicker, a bit thicker, a bit thicker, and a bit thicker. So this is just a sort of sanity check, so that you can make sure visually that your model works. Because sometimes you'll find that these mathematical expressions that you've used to generate the structure don't always hold true for any arbitrary combination of parameters. And so just checking through this in the beginning is a good idea to make sure that you have meaningful results at the end. Obviously, if you click start there, then your parametric sweep will start. You will be able to examine the results. Now, what I do suggest that you do, so is that your S parameters will look like this. You'll have a list of them here and they will sort of all be plotted together. Particularly when your numbers become large, it can be difficult to work with. Now, if you here in the post-processing tab, you have the option of you can export your S parameters as touchstone files, but instead of doing that manually, set up a template-based processing and have it done automatically. So here, template group will be S parameters, touchstone export. Number of samples, 101 is usually enough. You can have it as finely accurate as you wanted. Reference impedance 50 ohms. You can, if you like, remember that the waveguide impedance will not be necessarily 50 ohms. The one that's used here, I suppose it's close enough to 50 ohms. But because this isn't a line impedance, the 50 ohm doesn't really apply as such. So in this case, it just coincidentally happened to be close to 50 ohms. Okay, so now that that's there, that will export a touchstone every time we run the simulation. And so what will happen there is bring up an Explorer. Oh yes, of course. So first of all, what I'll need to do is save this project. Should have done this right in the beginning. I'm just to save it on my desktop and call it test1.cst. So that's a bit silly name. SW Duroid 6002 56 gigahertz. Give it a bit of a descriptive name so that you know what is going on. Save. Saving model. Okay, we run the simulation again, and if I bring up Windows Explorer desktop, so there is my CST file, and you'll notice that it's created a folder with the same name. In this folder there'll be result, and in result, once it's finished, these are the format that CST saves its own data in. The results will be saved, a new folder will be here called touchstone, and once it's finished, shouldn't take too long, inside of that will be all the touchstone files, numbered from 1 to however many runs you do, and in each case with the same name will be a text file with the parameter the parameters that we used in each of the runs. This is just helpful in identifying when you have looked at your touchstone files and you've decided which one you like the best. You can go and look at the equivalently named text file and find out what the dimensions were. And then what I usually do is just go back to CST, apply those parameters again, and run the simulation again, but with higher accuracy. So say instead of with 35 with 40 dB accuracy maybe, or perhaps more mesh cells, just to make sure that the result is as accurate as possible before sending it in for manufacturing. I think I have covered everything that I wanted to cover. That is the general idea, and you get a basic idea of the workflow in CST, of how to build a model, of how to simulate it, and how to interpret, to understand the results that you get. Incidentally, if you look at the S parameters while the thing is still working, you'll see that it generates some results, but they're not terribly meaningful because the port signals aren't finished yet. You see, for example, that the input signal is finished, the red one, but it hasn't finished analyzing the output yet. So it's best to put that away and not look at it until the end. Just want to wait until this finishes. So I can show you the touchstone file. What's taking so long this time? Right, I think that's what I've got to do. Okay, so yeah, in order to answer this question, if you wanted to change the material, that's easy enough. You just simply add a new material and then drag and drop over to whatever it is that you want to change the material of. if you wanted to investigate a different substrate, for example. The thicknesses, the parametric sweep I've covered, port modes I've covered, higher modes cutoffs I've covered as well. Yes. Okay, here we go. Okay, you will need to play around with CST to find some settings. With every model, it's different. I've mostly worked with SSW at lower frequencies myself. 56 gigahertz is a little bit high for me, and so but quickly enough you'll find some settings which are comfortable for you. For example, at 56 gigahertz, a 40 millimeter or 70 millimeter long board is far too long, and no real system will end up being that long. So it's probably a bit overkill. I just wanted to demonstrate just for demonstration purposes. So if you work with a smaller board, say 10 millimeters long, then your simulation time may go down. Also, it's not necessary to have all of this open space on the side of your SOW. Make it a little bit smaller, and that will obviously reduce the computational load on the computer and make your simulations go a little bit faster. Naturally, don't cut too many shortcuts or corners, because you want your simulation to be valid, a reflection of what your physical product will do, what its responses will be. Of course, there are many CST features which I haven't discussed in this video, but CST has very good documentation, among the best that I've ever seen of any software. Okay, so here result touchstone files. The TXT shows what parameter was there. It only shows substrate thickness 0.5 is because that's the one that was varied. If you vary more than one parameter, which you can do, obviously it just the amount of simulation that need to be done then increases exponentially with every parameter that you vary. In any case, the touchstone file looks like this. You can visualize it with MATLAB or any other numerical package that you like. AWR is an example. It also in the comments gives you a little bit of information about what's going on here. The units are in gigahertz. You are viewing S parameters in a polar format, and your reference impedance was 50 ohms. So this first number is S11, S12, S21, and S22. Now this number is linear, so it'll be varying between 0 and 1. It is not in dBs. If you wanted to get dBs, you need to take 20 log of this number. This number is in degrees. Again, this number is linear, and this one in degrees. So it's magnitude, phase, etc., etc. Okay, thank you. I hope this has been helpful.